is my great pleasure to have Richard Garner from Macquarie University kick us off on 24 hours. And he'll be talking about Sweedler duals of monads. Sweedler.
That's right. Well, thank you very much, Marcy. And thanks for the invitation to speak here. I'm going to speak about something which is only mildly off topic. So it's almost about operads, it's about monads. But, you know, it's not that far away. And I think it's quite fun and interesting, so I wanted to talk about this. So Sweedler duals. So Sweedler duals arise normally in algebra. So what is a Sweedler dual? So I start with the category of K-vector spaces. And that's got a monoidal structure on it, a well-known monoidal structure such that the linear maps from the tensor product of two vector spaces are the same as the bilinear maps from their product. And that's a closed structure, which means that whenever I've got a vector space, I've got a dual vector space just by homming into the monoidal unit. Okay. All right, and that gives you a functor from vector spaces up into vector spaces. And that functor, it turns out, is a lax monoidal functor with respect to the tensor product. So this is just a general fact. If I hom into any object in a monoidal category, that gives me a lax monoidal functor of this kind. And in particular, because it's lax monoidal, it sends monoids in k-vect op to monoids in k-vect. And a monoid in k-vect op is a coalgebra, and a monoid in k-vect is an algebra. So if I take the linear dual of a coalgebra, then I get an algebra. On the other hand, if I take the linear dual of an algebra, I don't get a coalgebra, okay? Because it's not kind of op-lax monoidal, this functor. However, what Sweedler showed, so this is in Sweedler's Hopf algebra's book from 1969, he showed that the functor that takes a coalgebra to its linear dual has an adjoint, okay? Now it's a contravariant adjunction, so depending on where you put the op, it could be a left or a right adjoint, but the way I've set it up here, you can see that taking the linear dual from coalg op into alg has a left adjoint, going from alg into coalg, okay? And the construction of this dual is a bit complicated, and I'm not going to go into that because this is really just going to be an analogy for something else, okay? All right, so now we're jumping forward 50 years to 2019. So there's a paper by Katsumata, Rivas, and Ustalu, and they describe a version of this that replaces algebras and coalgebras in k-vector spaces with monads and comonads on set, okay? So I start with the category end A set. So these are endofunctors of set, and the A there stands for accessible, which I'm not going to explain, but it's just a size condition that makes everything work. Okay, so it's a restriction on your endofunctor that you say that it's accessible. And this has a closed monoidal structure, which is similar to the monoidal structure on k-vector spaces in that you have a characterization of what the tensor product does. And so if I take two endofunctors F1 and F2, then their tensor product has the property that natural transformations out of F1 tensor F2 are the same as natural families, natural in X and Y, from F1X times F2Y into GX times Y. Okay? And so this gives you a monoidal structure, which turns out to be a closed monoidal structure. And so I can define the linear dual of an endofunctor F to just be obtained by homming into the identity. Okay? All right, as I said, if I hom into any object in a monoidal category, monoidal closed category, that gives me a lax monoidal endofunctor. Now, this is not what I'm using here, because you'll notice I said that this functor is lax monoidal with respect to not this tensor product, but with respect to a different monoidal structure, namely composition. Okay? So, I mean, there's some extra stuff you have to check that that's true, and it's part of the fact that really what we have on this category of endofunctors is a duoidal structure. But I'm going to skip over that, and the point is you could just check by hand that this is in fact a lax monoidal structure with respect to composition. And so what that tells you is that it sends monoids in here, composition monoids here, to composition monoids here. And a composition monoid in this opposite category is a comonad on set, and a composition monoid here is a monad on set. So there's always a linear dual of any comonad, which is a monad. On the other hand, if I take the linear dual of a monad, I don't get a comonad. But nonetheless, and so one of the important definitions in this paper of Katsumata-Risas and Ustalu is that of the Sweedler dual of a monad, which is again characterized by the fact that it gives you a left adjoint to this functor taking a comonad to its linear dual. Okay? All right. So you can look at these definitions and then you say, well, what's actually going on? What are these things that I'm defining? And so let's have a look. So first of all, suppose I've got a comonad on set. Can we calculate its linear dual? And well, yes, you can. So remember, the linear dual is just this internal Hom for this tensor product, and there's an explicit description of this internal Hom. And so we can just write down. So if I just start with an endofunctor, then its linear dual of F is F ring, where F ring of A is the set of all natural transformations alpha from F into blank times A. Okay? So that's just a definition you can make. And then from that, you can say, okay, and I suppose I start with a comonad, so it has a co-unit and a co-multiplication, epsilon and delta. Then I can turn this linear dual into a monad. And I'm not going to go through these formulae. They're here so you could sort of peruse them later. But you'll notice that the formula for the unit of this monad structure on the linear dual uses the co-unit of the comonad structure on Q. And the formula for the multiplication for this monad uses the co-multiplication for the comonad. Okay? And so that's all very much analogous with what happens for the dual algebra of a coalgebra. Okay? All right, but on the other hand, in the algebra case, finding the Sweedler dual of an algebra is quite hard, in the sense that there's not a kind of terribly explicit description. And so you might think, well, maybe it's going to be quite hard to describe the Sweedler dual of a monad, which remember is going to be some comonad on set. So in fact, it turns out you can give a very nice description of it, and my goal is to tell you what that nice description is. Okay? All right. So first of all, I'm going to give you a characterization of it, which isn't yet a calculation, but sort of tells you what the Sweedler dual of a monad must look like. And so to do that, we're going to have to just sort of step back and talk a bit about algebras and coalgebras for a monad. Okay? All right, so this is all very much analogous to what happens with operads. So all these definitions will look very familiar. So let's start by looking at monads on set. So throughout, we're just looking at monads on set. So, and these encode equational algebraic structure, such as groups, rings, vector spaces, lattices, or Boolean algebras, and so on. Okay? Importantly, it's structure where I'm allowed to kind of duplicate and discard variables. So, for example, in the axioms for a group, I say that x inverse is equal to the identity, and on the left, I duplicate x, and on the right, I discard it of that equation. So you can't express that via an operad, but you can via a monad. Okay, and just as you can take algebras of an operad in any K-linear category, so you can take algebras of a monad in any category that has products. So if C is a category with product, and I've got an object X in C, then I can construct a monad out of it called the endomorphism monad, which is a monad on set, and end C of X, I'm just giving you its underlying endofunctor, is the set of functions, sorry, no, I'm not. Yes, the underlying endofunctor end C of X takes a set A to the set of functions maps in C from X to the A into X. Okay? And so that's just the same as the endomorphism operad of an object in a symmetric monadal category. And in exactly the same way, I can then define a T-algebra for a monad on set on structure on the object X in C to be a monad morphism from T into end C of X. Okay? Now, if my monad T has a presentation, so it's generated by operation sigma I in T AI, subject to some equations E, then to give a T-algebra structure on X, basically I have to just give interpretations for these generators, which are going to be things sigma I from X to the AI into X, subject to the equations in E, where you have to interpret that appropriately, but that's not very hard. Okay? All right. Now, when I look at operads, I can look at algebras and I can look at coalgebras. And similarly for monads, I can look at algebras and I can look at coalgebras. So I can take coalgebras of a monad on set in any category with coproducts. And to do that, I look at the coendomorphism monad of an object X in such a category. And so that is really just the endomorphism monad in the opposite category. And so what it does is it takes a set A and it sends it to the set of functions in C from X into the coproduct of A copies of X. Okay? And so now I can define a T coalgebra in C to be an object X together with a monad morphism from T into this coendomorphism monad. And so that gives me a nice category. And again, if I've got a presentation of my monad via operation sigma I, then giving my T coalgebra structure, basically I just have to give maps in C from X into AI dot X, so the coproduct of AI copies of X, subject to the equations in E. Okay? All right. Now, we also have to, we're thinking about monads, but we're also looking at comonads on set. Okay? And so, and again, this is similar to the fact I can look at operads and I can look at cooperads. And so, when I look at a comonad on set, I can talk about coalgebras for that comonad. So, I mean, maybe you're not that familiar with comonads on set. They encode a huge range of structure. So, I mean, any Grothendieck topos with enough points is the coalgebras for a comonad on set. So you can get all sorts of things out of that. But for our purposes, we're going to think that a comonad on set encodes some notion of state machine. So coming from computer science, you have things like finite state automata or Mealy machines or Turing machines or stacks and things like this. And so these can all be encoded via comonads on set. Now, when we looked at monads, we could take algebras and coalgebras in any category we felt like. When we come to comonads, it seems that the only sensible thing you can do is to take coalgebras in set itself. Okay? It just seems to be the way it is. And just like before, we can do this in terms of something like an endomorphism monad, but this time it's a coendomorphism comonad. So given a set X, there's a comonad given by X times blank to the X. So that you can check is a comonad on set. And then I can define a Q coalgebra for a comonad on set to be a comonad morphism from this coendomorphism comonad into Q. Okay? All right, so we have these three different things. We've got monads and their algebras. Oh, what happened there? Monads and their algebras. That's interesting. I don't know what happened there. Just give me a minute. I better fix it. Okie doke. Here we go. And we're back. All good? Yeah. Okay. So let me undo that wild thing I just did and continue where we were. So we've got monads and their algebras, monads and their coalgebras, and comonads and their coalgebras. Okay, but when we talk about monads and comonads, we also have what's perhaps a more familiar notion of algebra or coalgebra, namely the Eilenberg-Moore algebras and coalgebras. Okay? So I've got a monad T on set, then normally when I talk about an algebra, I mean a set X with a map from Tx into X satisfying some axioms. And similarly, when I've got a comonad on set, a coalgebra would normally mean a set X and something from X into Qx satisfying some axioms. Okay? But that's okay because really these are two different perspectives on the same thing. So if I've got Eilenberg-Moore algebra, a set with a map from Tx to X satisfying axioms, that's the same as a algebra structure on X in set according to our previous definition. Okay? And similarly, if I've got an Eilenberg-Moore coalgebra, X to Qx, That's the same as a coalgebra for my comonad given by a map from the coendomorphism comonad into Q in the sense of our previous definition. Okay? All right, and so now remember, I start with a monad T on set. I can produce this Sweedler dual comonad. And so you might ask if somehow this Sweedler dual comonad can be characterized in terms of something a bit similar to these two things we see here. Okay, and in fact, that's the case. So this is what happens. So I've got my monad T on set. It's got its Sweedler dual comonad T bullet. And that's characterized by the fact that the Eilenberg-Moore coalgebras for the Sweedler dual comonad are the same as the coalgebras of my monad T in set. Okay? So set-based coalgebras for my monad are the same as Eilenberg-Moore coalgebras for my dual comonad. Okay? And, well, we can prove this. An Eilenberg-Moore coalgebra for the Sweedler dual, that's the same as a comonad map from the coendomorphism comonad into the Sweedler dual. But remember, the Sweedler dual is adjoint to the linear dual. So this is the same as a monad map from my original monad T into the linear dual of the coendomorphism monad of X. Okay? Now, before I showed you how to compute the linear dual of a comonad, and you can go away, and I also gave you the formula for coend X. So you can go away and you can plug coend X into that formula and use the Uneda lemma. And what you find is that you've produced this monad here. Okay, the endomorphism, or the coendomorphism monad of X. Okay, so the linear dual of the coendomorphism comonad of X is the coendomorphism monad of X. Okay, so in other words, this Sweedler dual comonad is the comonad that's induced by the adjunction between the set-based coalgebras and set. Okay? So to compute this Sweedler dual comonad, it's enough to describe what this category of coalgebras looks like. And so somehow this is much nicer than the situation with the Sweedler dual of a algebra. All right. So if you really hated this section, you can ignore it, because what I'm going to do now is explain to you how to compute the category of set-based coalgebras of any monad. Okay? And that's going to let us compute explicitly this Sweedler dual. Okay. And so it turns out to be as simple as you could possibly like. I mean, that's not true. You could probably think of something simpler, but it's as simple as you might reasonably hope. Okay? I start with any monad T on set. I look at its coalgebras in set. And they, it turns out, are just a pre-sheaf category. Okay? So let's see why. So I've got these coalg T set, and that has a forgetful functor down to set, where I just forget the coalgebra structure. And, okay, well, you might hope that this has some kind of adjoint, and yes, it does. It's got a right adjoint, and in fact, it's comonadic. Okay? And so the comonad it generates, by the discussion we had previously, is actually T bullet. All right, but we can say a bit more. So what is a T coalgebra structure on a set X? Well, remember, if T is a monad generated by these operations sigma I in T AI, then this T coalgebra structure involves giving functions from X into AI times X subject to the equations in E. Okay? All right, now if you look at that, this functor here, AI times blank, doesn't preserve all limits because it doesn't preserve the terminal object, but it does preserve all connected limits. Okay? All right, so our coalgebra is a set X with a bunch of functions like this. And so if I have a connected limit, if I have a connected diagram of coalgebras, then I can just take the limit of that diagram at the level of underlying sets, and I can lift the coalgebra structure to that limit. In other words, if I look at this forgetful functor u, it creates connected limits. Okay? And so what we found is that coalg T set is the category of coalgebras, Arlenberg-Moore coalgebras, for a connected limit preserving comonad on set. Okay? And the category of coalgebras for any connected limit preserving comonad on set is a pre-sheaf category. Okay? So maybe you didn't know that, but it's true, and it's kind of quite fun to work that out. But in any case, just by sort of looking at examining what a T coalgebra in set looks like, we've deduced that it must be a pre-sheaf category. Okay, the category of coalgebras is a pre-sheaf category. Okay, so then the obvious question is, well, what pre-sheaf category is it? And so our goal now is to try and answer that question. And to do that, we're going to suddenly take a view on monads, which is probably radically different from any existing within mathematics. And it's a view on monads which comes from computer science. Okay, so in computer science, we have functional programming languages like Haskell, and I don't know if many people here have used Haskell, but it's a functional programming language, and what that means is that basically you manipulate functions within it as first-class entities, and in particular, on the face of it, these functions can't really interact with the external world. Okay, I mean, if I look at the squaring function from natural numbers to natural numbers, there's nothing in the squaring function that allows me to prompt a user to input a natural number. Okay, it's just a thing that squares natural numbers. But when you're doing computing, if you don't have a way of taking the functions you describe and interacting them with the external world, then you're in big trouble. Okay, and so a sort of very famous paper by Eugenio Moggi from 1991 equated monads T, let's say on set for our purposes, with notions of computation. Okay, and so by a notion of computation, I mean something that takes the world where maybe I'm just doing purely functional things like squaring things and taking square roots or something like that, and moving into a world where I can do something that's a bit more interactive or interact with some external environment. Okay? And so the way this works is my monad T, elements of T of A, so I apply my endo functor to a set A, and I get a new set, which I think of as computations using this sort of extra interactive power coming from the monad T, and then returning a value in the set A. Okay, so let me try and give you an example of this. So T is going to be the free monad generated by a single Viary operation read. So V is some set here. Okay, it could be a finite set, could be something like the set of natural numbers, could be, you might think it's the set of strings that you could input from a keyboard or something like that. Okay, all right, so I take this monad, so an element of TA is supposed to be some kind of computation returning a value in A. And the kind of computation it is one in which I can request at any point during the computation a new value from V from the external environment. Okay? So it's a program which reads some V elements from an external environment and then returns a value in A. All right, now an element of TA can be, the elements of TA can be defined inductively, right? So they're either elements of A embedded via the monad unit, so it could be E to A, and that's supposed to correspond to a program, and that program just doesn't do anything, it just immediately returns the value A. Okay? on the other hand, an element of T of A could be my basic operation read applied to a bunch of other elements of TA, which I'm calling T sub V, indexed by the set V. Okay? Read is a V-array operation, so it takes V parameters. And so I'm viewing it as a function here from V into T of A. And I'm writing it using this lambda notation, which again comes from computer science. So this is just the function which, when given little v and big V, returns T sub V in T of A. Okay? So this is a compound term. And the program it corresponds to is one that first reads a value and then binds that to the identifier V and then continues as T sub V. Okay? All right. And so maybe an example will help illustrate this a bit better. So suppose V is the set of natural numbers. So then T of N is the set of programs which are allowed to request natural numbers from an external source and then eventually will return a natural number. Okay? So we could request, we could input two numbers from a user and then return their sum. Okay? And so here's a program which does that. So first of all, I do a read. The result of that read is n. And then given that result n, I'm going to continue as follows. I'm going to perform another read. I'm going to bind the result of that read to m. And then here, I return n plus m. Okay. So as I say, if you're familiar with this, then you've probably fallen asleep. And if you're not familiar with this, it's going to seem quite strange. But it's a very interesting other perspective on monads. If you like, it's one that rather than privileging the algebras, privileges the Kleisli category of the monad. Okay, so I'm just going to give you one more example of this. So this is what I call the theory of an inexhaustible stack. So stack is something that I can push and pop values from. And if I push a value onto the top of it, then when I pop a value, then I always pop the thing I pushed onto it last. Okay? So stack's inexhaustible if no matter how many times I pop things from it, it just keeps giving. Okay? So I can associate a monad on set to interact, which encodes interacting with an inexhaustible stack. Okay? And I'm going to suppose it's a stack of zeros and ones. Okay? So each element's either a zero or a one. And so how does this work? I take the monad generated by a binary operation pop and two unary operations called push 0 and push 1. And so maybe it's easiest if I explain what this all means by looking at what elements of T of A actually look like. So again, they're programs which can read and write from an inexhaustible stack before returning a value in A. And so just like before, if I have the inclusion of an element of A into T of A, then that's the program that just immediately returns that value A. If I've got an element which is of the form push sub I of T, okay, then that's the program that first pushes the value I, which could be 0 or 1, onto the stack, and then continues as T. And so finally, I've got this operation pop, which has takes two inputs. And that program corresponds to the following. First of all, I pop a value from my inexhaustible stack, which I can always do because it's inexhaustible. If I get a 0, then I continue as T. If I get a 1, then I continue as U. Okay? So, I mean, you can see that this thing here is actually analogous to this read operation previously where V is equal to 2. And I mean, indeed, it is this V operation when V is equal to 2. All right, but then there's some axioms here. The first axiom says that if I pop a value from the stack, so okay, this program here first pops a value from the stack. If it's 0, then it pushes 0 onto the stack and continues as X. If it's 1, then it pushes 1 onto the stack and continues as X. Now, I might as well not have bothered doing that, right? Because I pop a value off the stack and then immediately push it straight back on again, and in either case, continue as x. And so that should be equal to just x, okay? And then this axiom here says, if I first push I onto the stack, and then pop and continue as either x0 or x1, depending on what I see, well, I actually know what I'm going to see, right? I'm going to see I, because I just pushed I onto the stack, and so that should be the same as just continuing as xi. Okay? All right, good. So, maybe this is all a bit fierce, but at the very least, it'll give you something to chew over later. But I'm going to push on, and we're going to see what that has to do with these Sweedler duals. And really, it's because actually, when we view monads in this way, the coalgebras of a monad in set correspond to something completely natural from a computational perspective. And what they provide is an environment that allows you to run one of these computations. Okay? So let's just step back a bit. So here is our first example. And we had this little program here that read two values and then returned their sum. Now, this doesn't actually, I mean, there aren't any actual values that this reads. It's just a statement of intent. This is what this program is supposed to do. But at no point does it ever actually get fed any natural numbers and then add them up. It's a kind of syntactic statement that expresses a desire to do that. But we might want to actually do that. And the way we would do that, turns out, is via a set coalgebra for this monad. All right. So let's illustrate this. So what's a set? So remember this monad for Viary input, which just had a single Viary operation. It was freely generated by a single Viary operation. Okay. So that means that a set coalgebra is something super simple. It's a set of states. That's the underlying set of the coalgebra. And then I give something which is an interpretation of my generating operation. Okay, which goes from S into V times S, and that's it. Okay, so set coalgebra is literally that, because this monad is generated in such a simple way. All right, but we can interpret this as follows. What it does is it takes each S, which I think of as a state of an external environment, and I associate to S a value V from my set V, together with a continuation state, so a new state S prime. Okay. And so what we can view this as doing is, suppose I'm given an element little s in big S, and I'm giving some term t in T of A. So a term t in T of A is a computation which might request some values from an external environment, and then eventually return something in A. And the point is, each of these things is each of these terms t is going to give me something called interpretation of t from S into A times S. And what this does is it takes a starting state in big S, and it's going to return eventually a value together with the final state I reached in S whilst running my computation. Okay? And so, I mean, this interpretation is basically just, I know my monad's freely generated by this thing, and so if I know, so remember my coalgebra is a monad map from T into this coendomorphism monad, and so this datum here just tells me where my generator of my monad T goes, and then this thing here is telling me where all the other operations go, and so that's completely determined by being a map of monads. And if we work out what happens, so if I've got this computation which is just return A, and I run that from state S, then I'm just going to return the same state S and the value A, because that's what my program tells me to do. Okay, on the other hand, suppose that I want to run a program which is first reads, and then depending on the W it reads, continues as T of W. Suppose I want to run that program from state S of my coalgebra. Well, the way I do that is, first of all, I apply this basic operation read to my state S, and it returns a value V, whoops, and a new state S primed. And then in that case, to run this program here on the right, starting from state S, what I'm going to do, well, I set this W here to be equal to this V that I got over here, and then I evaluate TV from this new state S primed. Okay? So look, maybe this is easier if I give you a little example. So remember this program here, which is supposed to read two numbers and then return their sum. And suppose I run this starting from state S of a coalgebra. Suppose, moreover, in this coalgebra, if I apply my basic operation to S, I get 7 and S primed. And then when I apply my basic operation to S primed, I get 22 and then S double primed. Well, in that case, what my environment is doing is, starting from state S, it's the next value it gives you is 7, and it continues as S primed. And then starting from state S prime, the next value it gives you is 22, and then it continues as S double primed. Okay? And so what's the effect of running this program starting from state S? What happens is, well, first of all, I request an input value, which is 7, and I call that N. So now I'm in state S primed after having got that 7, and so I request another input value, and I know that that has to be 22, so I call that M. And then I'm going to return N plus M, which is 29. All right, but I don't just return 29, I also tell you the final state that I reached, and that's the state I get here after applying my basic read to the state S prime. Okay? Okay. So, in a similar way, we can talk about what a coalgebra for the monad for an inexhaustible stack is. Well, again, it's a set of states, which indicates the sort of current state of the environment. There's a function pop, which in any given state returns the value 0 or 1, which is on the top of the stack in that state, and then moves to a new state, which encodes the stack with that 0 or 1 removed from the top. On the other hand, I've got functions push I from S to S, and what that does is in a given state S, it returns a new state S prime, such that the state, if S encodes a particular version of the stack, then S prime encodes the version of the stack that's had a 0 or a 1 added on the top. Okay? And this condition here is just what the equations for the theory of an inexhaustible stack impose. Okay? And then maybe I won't go through this, but much as before, any term of the monad generated by this, which is a little program which can read or write from that stack, has an interpretation which, given any starting state of the stack, performs some reads or writes, and then eventually returns a value in A and the final state of the stack. Okay? Okay, good. So, using this, we can actually now start to remember our goal is to try and describe this category of coalgebras associated to a monad T and set. Okay? We want to show its pre-sheaf category. And as an important step towards that, we're going to try and work out what its terminal object is. Okay? We know it's got a terminal object if it's a pre-sheaf category, but we'd like to be able to write it down. Okay, and so the way we do this is via what we might call the behavior of a given state of a coalgebra. And so what the behavior of a given state is a function which to any element of TA, which is a computation returning values in A, gives me an element of A. And what is that element? Well, it's the element that I get if I run the computation TA starting in state S. Okay, so remember this example here. So here, this state S assigns to this little element of Tn here the value 29. Okay, so that's giving me a function from T of n into n, sending this to 29. Okay, and so in general, I can take any state of a coalgebra and I can assign to any T computation returning values in A the value A that I get by running that computation starting from state S. And that's exactly the first projection of this interpretation function of T applied to the state S. Okay? So it now turns out that if I have two states of a coalgebra in set, then these behaviors, so the values in A that I obtain by running any computation from state S or from state S prime, if those will coincide if and only if my two states map to the same element in the final object of this category of coalgebras. Okay? So the final object encodes precisely the behaviors that you might observe externally for two different states, for a given state. And in fact, this allows you to describe the final coalgebra very explicitly. So remember, each state has associated to it a natural transformation. And so you can ask which natural transformations arise in this way from states of any coalgebra. And it turns out that there's just a single condition you can write down which ensures that this is indeed the case. So I just take a natural transformation from T into the identity functor, satisfying the following equality here. Okay, and what does this say? This says if I run a computation T, and then depending on the output value A that I observe after running that computation, I continue by running a computation UA. That should be the same as running the computation T, ignoring the output value, and then running the computation U of beta of T. Okay? So beta of T tells you the A that you get here once you run T. Okay? So this condition turns out to characterize exactly the things that can arise in the form beta S, things of the form beta S. And so now what you can prove is the set of all such admissible behaviors is the final T coalgebra. So there's a formula here for the interpretations of all the operations in this final coalgebra. Okay, and so you can go away and you can figure out what these final coalgebras look like in examples. And what you find, for example, is the following. So the final coalgebra of the theory of V-valued input. So basically it's telling you the possible things. So if I imagine one of these coalgebras for V-valued input, what can it do? Basically, when requested, it can give you a value in V. Okay? And so starting from any state, I can get a stream of values in V, indexed by the natural numbers, just by, well, I request a new value in V, and then I continue as a new state. I request a new value in V, and then I continue as a new state. And the observable behaviors I get from that are just the values in V that I get by this process. Okay? And so I get V to the n. And so the coalgebra structure associated to the set V to the n is the following. Well, if I've got a behavior, which is just an infinite stream of V's, and I request the next value in V, well, I just return the first element of that stream, and then the remaining state is just the rest of that stream. So I knock off the top element, and I just return the rest of it as my continuation state. Okay? And it turns out for the inexhaustible stack, you get something pretty similar. So this is v to the n. Here I've specialized v to be 0, 1, and I get 0, 1 to the n. And this operation here is the same as this operation here. And then this bit here is kind of an inverse for that operation. All right. So we've now got some idea about what the terminal object in this category of T coalgebras is. So our goal now is to try and understand what the general T coalgebras look like. Okay? And, well, turns out they're determined by slightly less data than you might think. So I've got a general T coalgebra S. So it's a set of states, and for each term T in TA, I've got an interpretation T of S, which is going to be an element, gives me an element in A together with a new state in S. Okay? Now what is that? The first component by definition is the behavior of my state S when applied to the term T. Okay? The second component here, I can describe it as, so this is this T twiddle. What's T twiddle? So T is some program in TA which does some computation and then returns a value in A. Now you can imagine running that computation, returns a value in A, but then I throw that value in A away. Okay? And so that gives me something, a new computation in T of 1. In T the same. Okay, so T twiddle in T of 1 is, if you like, the image of T in TA under T of the unique map from A to 1. So it's the result of contracting all the variables in my term T. Okay? And so the continuation state I get from S by applying T is really the same as the continuation state I get by taking S and applying T twiddle, because T twiddle just does the same stuff as T, but it throws away the return value in A. Okay? And so what's the conclusion? The conclusion is that to describe the coalgebra, it's enough to know what the behavior is associated to each element S, and moreover, how the unary operations of my theory act on states S. Okay? So there's two little bits of data to determine everything about the coalgebra. Okay, but they're not independent, these two structures. So I've got this action by the monoid of unary operations and the behaviors associated to each state. But the behavior in a given state constrains the way that the unary operations of the theory can act on it. Okay? So here's an example. Suppose I've got a coalgebra of the theory of an inexhaustible stack. So each state S encodes a particular state of an inexhaustible stack of zeros and ones. Okay? And suppose I've got some state S, and suppose that when I do a pop from that state, the value I get out is 0. Okay? So the top element, in this state little s in big S, the value on the top of the stack is a 0. Okay? All right. So suppose I'm trying to move from that state S into a new state by running some unary operation on it. Okay? So this one here, the one in the middle, pop XX, simply pops the top element of the stack and doesn't do anything else. Okay? This one to the left here, let's do the one to the right. This one to the right pops the top element of the stack. If it's 0, then it stops. If it's 1, then it pushes a 0 onto the top of the stack and then stops. This one to the left, on the other hand, pops the top element of the stack. If it's 0, then it stops. If it's 1, then it pops another element of the stack and then stops. Okay? Now, if I take these three unary terms and I use them to act on a state S in which the top element of the stack is 0, then I always end up taking this left branch. Okay? So I end up popping the top element and then not doing anything else. And so all these terms have to act in the same way on my state S. All right. Okay, and so this motivates a definition. I've got a monad T. I've got some possible behavior of a state of a T coalgebra, which is beta. And using that, I can define an equivalence relation on the unary operations of my theory, which is such that, it's basically such that in this example here, all terms like this get identified because they're the same in their left component. In their right component, they're different, but for a state where the first thing I read is a 0, it doesn't matter what the right component looks like because I'm going to ignore it anyway, because I'm always going to continue in the left-hand branch. Okay? So given this possible behavior, I define beta equivalence as the smallest equivalence relation on T1 such that, so here I've got a term T and I substitute in a bunch of other terms. And here I've got the same term T, but I substitute in a different bunch of terms V. Okay? All right. And I've got some given behavior beta. And suppose that in this behavior beta, when I run it on term T, I get some beta T in A. And so suppose that the A components of U and V are the same. So what that means is that when I run this thing here, starting from state beta, the first thing I do is figure out what this A should be. And to do that, I apply beta to T. And so I get, this will reduce to U beta T. And this will reduce to V beta T. And so if U beta T is equal to V beta T, then I'm always going to end up doing the same thing. Okay? And so the little lemma is that if I've got a state of my coalgebra that has behavior beta, then whenever two unary terms M and N are beta equivalent, they'll always act in the same way on my state S. Okay? Okay. So I've now finally got enough to get towards describing this, this coalgebra category. So sticking all of that together, what we discover is the following. To give a set S, coalgebra structure for a monad T is the same as giving the set S, together with a map down to the set of possible behaviors. So remember, that's the final T coalgebra. So just a function down to there, and a right action by the unary operations of the theory, such that, so first of all, there's some condition here that says that if I take a state S and I act on it by unary operation, the behavior of S.M should be related in some natural way to the behavior of S. And then the second condition is that if I've got two terms which are such that the behavior, if I've got two terms which, with respect to the behavior beta S, must act the same, then they do indeed act the same on S. All right. All right, so now if you look at this definition, if you want, you can ignore everything I told you before now and just look at this definition. And you can observe that these data here are actually the data of a pre-sheaf. Okay? And the data of a pre-sheaf are the following category. The category with object set B, and I've got a map from S to B, and a pre-sheaf on a category involves a set with a map down to its object set of that category. So that's good. And what are the HOM sets? Well, the Hom set from beta to beta prime is all the unary operations such that this thing here applied to B gives me beta primed, but quotiented out by this equivalence relation of beta equivalence. And so now what we can say is that if T has a behavior category B, then the category of T coalgebras in set is isomorphic to this pre-sheaf category, B set. Okay, and it turns out that you get something quite interesting. So I get a category canonically associated to any algebraic theory, or any monad on set. So for example, I take this, the theory of V-valued input, just generated by a single Vieri operation. And so this category, what does it look like? The object set are all the n index families of elements of V. And a map from W to W prime, basically there's a map from W to W prime if W prime is obtained from W by deleting some initial segment. Okay? On the other hand, for this example of the inexhaustible stack, what does this category look like? So the objects are just all the infinite binary strings. Okay, and those encode the possible states of an inexhaustible stack, right? I mean, an inexhaustible stack is supposed to just be a big thing with lots of zeros and ones, and I can sort of remove and add elements from the top end. And what's a map from W to W prime? Well, basically, it's something which encodes the manner in which I might remove or add elements from the top end of a stack. Okay, so this says I start with my stack with this stream of values in W in it, and I'm basically going to remove some initial segment of my stack and then add on some new initial segment, because I'm basically, I mean, in the end, I'm doing a bunch of pushes and pops. And so that's going to, in the end, result in removing some bunch of stuff from the front of the stack and adding some bunch of other stuff onto the front of the stack. Okay? And so that's what we get here. A map from W to W prime is an integer I such that if I take W and shift it by I, then eventually, if I go far enough along it, it's going to look like W prime. Okay? So another way of saying that is I take W, remove an initial segment, stick on a new initial segment, and I get W prime. And this integer I encodes how many bits I had to remove or stick on. Okay? And so we can stick all of this together, and hey presto, this is what I would describe as a pretty explicit formula. You might find it slightly too explicit, but the nice thing is that somehow you don't really expect to be able to write something down that's this kind of on the nose description of something like a Sweedler dual. So in the algebraic case, I mean, the best thing I can do is say, well, it's the union of all its finite subcoalgebras, and I can describe its finite subcoalgebras in this way. But this is somehow, I mean, it's just here. I've just written it down. So yeah, that's kind of, I don't know, I find it very surprising that you can do this in such a concrete way. All right, so I said that if I had time, I'd talk about topological case, and I clearly don't have time, so I'm not going to talk about the topological case, except to tell you that there's a version of this, there's sort of Sweedler duality between monads on set and comonads on topological spaces. And correspondingly, this category B associated to any monad T can be turned into a topological category whose domain projection is a local homeomorphism and whose base space is pro-discrete. So, I mean, for example, a stone space is pro-discrete. It's a projective limit of discrete spaces. And I just want to mention this because if I look at this theory of an inexhaustible stack, then when I topologize this, this category B associated to it, objects are these binary strings, maps add or remove initial segments. When I topologize it, I get this thing called the Kuntz et al. Groupoid, which is something that turns up in the theory of C-star algebras. So this Kuntz C-star algebra O2, which turns up in physics and representation theory and all sorts of other things, can be generated from a certain et al. Topological groupoid. And it turns out that it just pops out of this theory of an inexhaustible stack, just very directly. Okay, great. So I'm probably going to stop there. And here's just a few references that you might find useful or interesting. Okay, thank you.
Thank you, Richard. That's really excellent.